Welcome to While We Were Distracted, the podcast where we explore topics that often get overshadowed in the rush of daily life.
We are really thrilled to have you with us today as we tackle, an incredibly dense and honestly slightly eerie scientific breakthrough.
Yeah, it definitely borders on science fiction when you first look at it.
It really does. Our mission for this session is to unpack a fascinating intersection where biology fundamentally meets classic video games.
Right.
We're going to be pulling from a widely circulated excerpt titled The Digital Synapse, Biocomputing and the Biosilicon Doom Engine, and we're also synthesizing that with some official announcements from an Australian biotech firm called Cortical Labs.
And we really need to look at the technical realities behind a certain viral video that's been dominating tech circles lately.
Exactly. Because for everyone listening who tracks hardware evolution, we're looking at a scenario that challenges the very foundation of how we build processing architectures. I mean, what if the next major leap in computing isn't made of silicon, but of living brain cells?
It forces us to entirely reevaluate the traditional architectures we've relied on for decades. We're looking at a fundamental departure from binary processing.
Okay, let's unpack this, because to fully grasp the leap Cortical Labs has achieved here, I feel like we have to start with the cultural moment that brought this whole thing into the mainstream.
The viral reel.
Right, the reel. So on March 4th, 2026, there was this account operating under the handle at 0x Subversion.
Subdot version, yeah.
Yeah, and they posted a reel that just immediately sparked intense debate. Like, the footage showed what looked to be this complex, fleshy biological culture hooked up in a highly controlled lab interface.
And it was wired directly into a visual output running Doom, the 1993 IDE software classic.
And the crazy part is the biological mass was actively navigating the game engine.
Yeah, the visual is striking. It naturally triggers a lot of innate sci-fi alarms for anyone watching.
Oh, absolutely. The immediate reaction online leaned heavily into some dark dystopian speculation.
Naturally. But analyzing the actual tech requires us to step back and look at the official documentation that Cortical Labs released just before that viral leak happened.
Right. This was around February 25th and 26th of 2026.
Exactly. The footage from that reel is actually just a direct capture of their new CL1 biocomputer in action.
The CL1. And the hardware specs on this are where it transitions from a conceptual experiment into a viable platform. We're talking about an architecture utilizing approximately 200,000 lab-grown human neurons.
200,000.
Yeah. And these cells, these metabolically active cells, are physically integrated with high-density silicon tracking hardware.
Which creates a hybrid processing unit that the industry categorizes as wetware.
Wetware, which is just such a wild term.
It is, but the integration itself is a massive engineering feat. The architecture relies on what's called a multi-electrode array chip, or an MEA.
Right.
The stem cell-derived neurons are cultivated directly onto the surface of this MEA chip, and that interface essentially acts as a high-fidelity translation layer.
So it's basically taking biological signals and turning them into computer code.
Basically, yeah. The microscopic electrodes embedded in the chip detect the tiny voltage spikes, the action potentials generated by the cells.
And it operates bidirectionally, right?
Yes.
Like, the MEA doesn't just passively listen to the cells. It can actively stimulate them by injecting targeted electrical impulses back into the biological tissue.
Which is how it bridges the gap. It translates the digital state of the Doom engine into an electrical language the neurons can process.
And then translates their biological responses back into digital keystrokes to move the character in the game.
Exactly. To put this in perspective for you, the latency requirements and the signal-to-noise ratios involved in a bidirectional interface of that scale are just immense.
I can imagine. Trying to filter out random biological noise to isolate deliberate firing must be incredibly complex.
It is. Yet they achieved an interface reliable enough to facilitate actual active learning.
Which brings us to the training phase. And this is where the data gets truly staggering. They successfully trained this network of 200,000 neurons to operate within a simplified version of the Doom environment.
And they did it in a week.
Just 7 days. The wetware network learned to navigate the 3D space, track targets, aim, and shoot enemies.
And this isn't pre-programmed logic. The biological cluster had to actively decipher the environmental mechanics on its own.
How do they even do that? How do you tell a clump of cells to play a video game?
What's fascinating here is the underlying mechanism driving that adaptation. It leverages a foundational concept in biological thermodynamics known as the free energy principle.
Okay, break that down for us.
Well, the researchers didn't write a script for the cells to follow. Instead, they designed a system of electrical rewards and punishments that exploits how biological systems naturally want to minimize internal chaos, or entropy.
Right, so they mapped the visual state of the game into electrical pulses fed directly into that MEA chip. And when the neurons executed a good action like successfully hitting a target in Doom, the system gave them a highly structured, predictable electrical pulse.
A low entropy state. It's calming for the cells.
Right. But conversely, if the network failed or navigated poorly and took damage in the game,
The MEA flooded the neurons with chaotic, unpredictable electrical static, a high entropy state.
and biological networks hate that. They are inherently driven to seek equilibrium.
Precisely. To avoid the chaotic static, those 200,000 neurons rapidly rewired their own synaptic connections. They physically altered their network topology to consistently trigger the predictable feedback instead.
They basically optimize their internal architecture to maintain a stable environment. It's like a hyper-accelerated version of natural adaptation.
It is. The network learns the rules of Doom simply because mastering the game is the most efficient path to achieving electrical peace and quiet on the chip.
That's incredible. The cells aren't actually playing a game. They're solving an environmental puzzle to minimize sensory surprise.
It's a brilliant application of neuroplasticity. And if we look at the timeline, it shows a really aggressive scaling of complexity.
Because this isn't their first rodeo.
No. This CL1 is a direct evolution of Cortical Labs' 2022 milestone, the Dish Brain project.
Right, where they use a similar setup to play Pong.
Exactly.
But the jump from Pong to Doom in just 4 years is an exponential increase in spatial complexity.
Oh, massively.
I mean, Pong is just calculating a simple, highly predictable 2D vector. It's a closed loop. But Doom...
Doom is a continuous 3D visual field.
Yeah. The network has to abstract spatial depth, object permanence, movement tracking across multiple axes, and immediate threat prioritization.
The cognitive load required to maintain equilibrium in that dynamic engine is orders of magnitude higher than just predicting a bouncing square.
Which proves that wetware isn't restricted to just simple binary reflexes. It can handle real-time abstraction.
And complex pattern recognition in highly dynamic digital environments.
Okay, but this forces us to ask the obvious question on everyone's mind. Why go through all the trouble?
Why use living cells instead of standard computer chips?
Exactly. Building and maintaining a metabolically active processor is inherently difficult. You have to manage incubation, nutrient delivery, biological degradation.
Variables that just don't exist in pure silicon.
Right. Given how powerful modern semiconductors and AI neural networks are today, the value proposition for biological processors has to be overwhelming.
And it is. The rationale hinges on two massive bottlenecks currently facing the traditional silicon roadmap: extreme energy consumption and the inefficiencies of how artificial learning actually happens.
Let's talk about the energy first, because the thermodynamic cost of modern computing is becoming entirely unsustainable.
It really is. Training and operating large language models requires gigawatt-scale data centers.
We are dedicating the electrical output of entire power plants, plus immense water cooling infrastructure, just to keep silicon chips from melting while they brute force mathematical weights.
And the von Neumann bottleneck is partially to blame for that.
The separation of memory and processing.
Right. Traditional computing wastes a ton of energy just shuttling data back and forth between the memory modules and the central processing unit.
But biological networks don't separate those functions.
No. In a biological neuron, the processing and the memory storage occur in the exact same location, the synapse.
And the power envelope reflects that efficiency. I mean, the human brain operates on a continuous power draw of roughly 20 watts.
Which is practically nothing.
It's performing incredibly dense, multimodal computing on a fraction of the energy required to power a standard laptop.
And the CL1 inherits that biological efficiency. It processes Doom using metabolic energy that barely registers compared to a silicon-based GPU cluster running the same machine learning parameters.
So it's incredibly energy efficient. What about the learning speed?
That's the second disruptive advantage. The biological processor inside the CL1 actually adapts significantly faster than a purely artificial neural network tasked with a similar parameter space.
Because traditional machine learning relies on things like backpropagation. You have to feed an AI millions of iterative examples over thousands of training epochs.
Slowly adjusting the artificial weights until it converges on a solution. It's effective, but it's mathematically rigid. and incredibly slow.
But biological neuroplasticity is different.
Very different. Wetware is capable of something much closer to one-shot or few-shot learning.
Because the cells physically remodel their synaptic connections in real time.
Exactly. To adapt to that free energy principle we talked about, they don't need millions of iterations. The CL1 mastered Doom in just 7 days.
Biology has spent millions of years optimizing adaptation, and now we're harnessing a system that learns faster than silicon currently can.
If we connect this to the bigger picture, we're looking at the foundational architecture for the next generation of artificial intelligence.
And bridging the gap between biological efficiency and artificial intelligence.
Right. We aren't necessarily going to see wetware replacing the silicon in your smartphone anytime soon.
That would be a bit messy.
A bit, yes. But we are looking at hybrid processors, where the heavy dynamic pattern recognition is offloaded to biological networks. We can circumvent the physical thermal limits of silicon by adopting the rapid plasticity of living tissue.
But introducing living human brain cells into computing environments naturally brings up a lot of Matrix vibes.
It does. It shifts the conversation toward ethical boundaries very quickly.
Yeah, the internet's reaction to Cortical Labs' YouTube demo, which was literally titled, "Living Human Brain Cells Play Doom on a CL1," generated immediate pushback.
When dealing with the public, the optical presentation of wetware requires very careful management.
If you look at the comments, there's a recurring theme calling the experiment torture.
The electrical stimulation aspect.
Exactly. There's this visceral discomfort with the idea of living human tissue being subjected to chaotic electrical static to force compliance.
It taps right into those dystopian brain-in-a-vat scenarios.
It does. But we need to clarify the reality here. We have to explicitly lay out the ethical facts from our sources.
Absolutely. The ethical parameters governing the CL1 are very clearly defined, starting with where the cells come from.
Right. The 200,000 neurons utilized in the array are derived from stem cells.
Induced pluripotent stem cells, yes. They are cultivated entirely within a controlled laboratory setting.
Meaning they are not taken from born humans.
Exactly. And more importantly, we have to address the state of the cellular cluster itself. A network of 200,000 lab-grown neurons is not sentient.
It's not a full organism.
No. It lacks the vast macroscopic architecture, like a cerebral cortex or a limbic system, that is biologically required to generate consciousness or to process the subjective experience of pain.
So it doesn't feel pain the way a biological brain does?
Not at all. It's essentially a collection of metabolically active logic gates. When the system delivers the chaotic static as a punishment, the cells aren't experiencing fear or suffering.
They're just operating under biological physics.
Right? Seeking equilibrium by adjusting their synaptic weights. Suggesting the cells are suffering is really just a projection of human emotional states onto a microscopic biological mechanism.
And to their credit, Cortical Labs is being very transparent about this, which helps mitigate the dystopian horror narrative.
They aren't treating the CL1 as some proprietary black box tech.
Right, they even put the open source Doom code they used on GitHub for anyone to see.
Operating via open source protocols is crucial when introducing technology this radical. Allowing the broader scientific community to audit the code ensures the development proceeds with necessary oversight.
So, what does this all mean?
It means we've crossed a major threshold.
Yeah, we are looking at a real functional biocomputer, one that uses 200,000 neurons to play Doom, proving that wetware can be faster and more energy efficient than pure silicon AI.
And it does so without crossing the line into sci-fi horror.
Yep.
The ethical guardrails are firmly established with non-sentient lab-cultivated clusters.
It completely shifts how we approach processing power.
But the success of this architecture forces us to look beyond a digital simulation like Doom.
Where is this heading?
Well, the CL1 is a proof of concept operating with a network smaller than a grain of rice.
Right.
So the real question for you to ponder is what happens when this wetware scales up?
Oh, wow.
If a mere 200,000 lab-grown neurons can master a digital environment like Doom in just a week using a fraction of a watt, consider the implications of scaling that up to millions or billions of cells and tasking them with managing real-world physical systems.
Like what kind of systems?
Think about the highly efficient smart grids or complex traffic networks of our near future. Could those immense computational loads be entirely offloaded from power-hungry server farms and instead be run by highly adaptable, metabolically efficient biological processors?
So rather than silicon algorithms, our cities could be managed by living tissue. That is a staggeringly complex proposition, but it entirely rewrites the roadmap for future technology.
It really does.
Well, thank you for joining us today as we navigated this incredibly dense breakthrough. We hope this deep dive equips you with a solid framework to evaluate biocomputing as it continues to evolve.
There's a lot more to come.
Definitely. Keep tracking the hardware, stay analytical, and always stay curious.
Don't forget to like and subscribe for the next episode on While We Were Distracted.